Hello YouTube, all of my, however many people are watching. Tonight I'm going to be doing some more circuit design. I've picked out the drive circuit that I'm going to use to drive my Nixie tubes, and so I'm going to be doing up a schematic symbol for that. I'm going to do the footprint for it, and then I'm going to put it in my circuit and get ready to drive some Nixie tubes. So, the component I've picked to do the driving is an HV5622, and it's a 220 volt open drain shift register. Sort of an odd and unusual part. It looks like it's designed to do like print heads and electroluminescent displays and other things that need not a lot of current but very high voltage. And so I'll need to make a schematic symbol for this, and then I will make the matching footprint, set them up, and then I will put this in my circuit and we will be driving some Nixie tubes. So I'm going to read through the schematic sheet here and see if they have any symbols that might be useful. I don't see anything of particular interest here, but generally if you're making a symbol it's easier to make something that looks like what's in the datasheet. In this case, this is about the closest thing to an overall schematic symbol they've got. So I'll probably do something where I put the different inputs on one side, the outputs on the other side, and my supply and ground voltages on the top and the bottom. So my CAD software of choice, as previous viewers will know, is Circuit Studio. It's Altium's mid-range product. It's not as nice as the full-priced version of Altium, but it costs a great deal less. So I will make a new component, and then I can start to put down some pins. I realize now that I have no idea what the pin map for this is, and that if I'm going to be doing this, I need to find that. So I'm going to pull up the pin map here. I'll place this in the chat so you guys can follow along, if anybody's actually watching. But, I have 2 viewers. Holy cow. So I'm going to bring this up, but I'm going to put it on my second monitor so that I can work on the first monitor. Oh, hello Katrina! You are watching me. You're watching me do the circuits. Neat. So, this is an HV out 22 for pin 1. If I place the second pin, it'll be HV out 21. I'm going to place these and then rearrange them once I have a better idea of how much space they'll take. Unfortunately, it's trying to number them sequentially in the wrong order. My phone is going nuts over here. I'm going to try to turn this off so it doesn't bug me while I'm... We'll see if that's any better. Nope, that's not any better. Okay, it's going in my pocket where it won't bug anybody. This particular chip has 32 outputs on it, so I'm going to be here for a couple of minutes. Just so let's see. The scrolling on this is a little bit too sensitive for my liking. Now I can start putting down the other half of the chip. So there's a data output pin, which is pin 23. 24 is, okay. Clarity, pin 27. Clock is pin 38. VSS, also known as ground. VDD, also known as supply voltage. Latch enable. Data in. BL is a blanking pin. And then the remaining pins, lucky for me, starting at pin 35 are, oh, nope. Still numbered in the opposite order. $29, $28, $27, $26, $25, $24, $23. My spacing was almost perfect. I think I got the pin numbers on these wrong, because this last one, oh no, that came out to pin 44. Alright, so that's 23, pin 44, and I can check this by looking over here. Here's my name, here's my designator, and I can just click these one at a time and double check that the signal names and the pins all line up. Some of these, it's not the end of the world if that's a little bit off. but for the data pins and stuff, it's going to be really important that I get those right. If I swap one or two of these high voltage pins, it's just a software fix. And I'll probably even wind up doing some pin swaps on these so that whichever pins I have connected across will just be designed to run straight to straight across the top of the board to the Nixie tubes, and then I'll map individual numbers to pins in software. That makes the PCB routing a lot easier. So I'm going to double check these. 3, 17, is pin 8. And HV11 is pin 12. Yep. $21, $22. I'll move those down, and now they're all in one block. That's a very large schematic symbol. So I'm going to put the control lines at the top. I'll put the clock, data in and data out just below that. And mostly this is chosen so that when I get to the point of putting these on a PCB or on my schematic, they'll look half decent. So now I'll put a background rectangle on this just to kind of tie the whole thing together. There we are, and come on, send to back. Better. Alright. This is that. This is an HV5622. I'm going to go borrow DigiKey's description. And then I will add a supplier link to this for DigiKey. So there's my DigiKey part number. And this is the 44 PQFP version, so it looks roughly like this. Alright, so now I need to draw a footprint for this. Let's see if there's enough data on their data sheet here to draw this package. There it is. And do they have units on this? Millimeters. Alright. Millimeters. Next. They have package drawings, but no footprint drawings. That is Unfortunate. PQ, FP footprint. I found a microchip section on this. Unfortunately, their changelog says they revised the 44-pin PQFP footprint in February 2007, and then in March of 2007, they removed it. So that doesn't help. Let's see if I can find the original data sheet for this. So this used to be a part from a company called Supertex, and Microchip bought them. Let's see if their schematic or their data sheet has a better footprint. It's a nice footprint, but it's got no dimensions on it. Okay. It helps if I type the footprint name right. Different part, same package, still no footprint. So that's a part, that's a part. This person complains about the footprint being not quite the same as another part, but doesn't have any references. Supertex product catalog. Here's another Supertex part. Again, no footprint. this is a PQFP. It doesn't show up on that page. Google, L is not P. I don't know what you're trying to do here, but it's not helping. Does this site have a QFP drive? Metric quad pack, flat pack. Interesting. Let's see if Microchip has anything on their site that looks similar. PQF pack. Microchip? There's something you're not telling me? Is this package a bad idea? So they've got two MQFPs here. Drawing number CD C04071. And they've got a TQFP as well. So this is 10 by 10 by 1 millimeter. And their MQFP is 10 by 10 by 2 millimeters. Dimension A here is nominally 2 millimeters. Very close anyway. Yeah, dimension A2, which is the height of the package, is 2 millimeters. So that's probably an MQFP. No, it says PQFP. And as long as the pads land in the right spots and with about the right amount of sticking out on each side, then it'll work. So Okay, well now let's... Page 124, huh? So let's compare this against this drawing and make sure that they're at least close. So, and then this contains a footprint that I can actually replicate. That should be pretty close. So, this is nice. Most of these dimensions are similar. Okay. So there's dimension A is the overall height, 2.45, 2.35. Okay. Dimension E here, same as E here, is 0.8 millimeters, 0.8 millimeters, that's good. These dimensions D and E are the overall size of the package, the overall distance between the ends of the leads. And those should both be 13.2. And here D and E correspond to the same measurements. 13.9. So this claims that the leads stick out a little bit farther. Let's see, D1 and E1 on both of these are referring to the same dimension. Here they're 10 and 10. And here nominally 10, nominally 10. Okay. So those are the same. So this package, the leads come out slightly farther. And then this dimension L1, distance from the package to the end of the lead, and here it's the same. So I'd expect L1 for this package to be longer, and if I look, L1 here is 1.95, and here it's 1.6, so yeah. They look like they're similarly sized, but the leads on this package are slightly longer. There was another variation of this as well, a KW variant. D1 and E1, these dimensions are the same, the pitch is the same, the lead length is the same as the previous, so this is... I'm not sure how this differs from this KW variant differs from the other variant. So if this lead length is 1.95 and this is 1.6, I need to make my leads 0.35 millimeters longer. Which means that when I make my pads, I need to make this length slightly longer. So I can work from this and then make things slightly bigger. So I'll put that off to the side, not covering the chat window, and go from there. A little bit of arranging over here so I can see things. Alright. I'm just going to do all these pads by hand because I can. We'll start with pad number 1. They're going to be, so this says Y1 should be 1.95, but plus 0.35 is 2.25. The other dimension is going to be 0.55. And I'm using a rounded rectangle pad because that seems to be the current recommendation in the industry for. And so this was recommending fully rounded pads. I'll do fully rounded pads. The square corners on some of the older pad layouts create a stress point that can be problematic for a lot of parts, and it can be the first point, basically that stress point at that corner, is where your pad will start to peel off the board, or where you'll get a crack that can form in the silk screen, or a bunch of other fairly subtle but really annoying problems if they actually happen. What am I doing? I'm on metric. I want my grid to be, I think I'm going to go with an 0.4 millimeter grid. So I can just drop these on 0.8 millimeter centers. And then come back and move them later. So if this is a 44 pin package, I'm going to have 11 pins to a side. Oops. Clearly, I need to do a little bit more counting here. Said all move. Come on. We're all going for an adventure. Goodness. Really? Well, so be it. I should be able to select and move all of these at the same time. So now I'm going to move around the perimeter. Just keep putting down more pads. 22. I'll come back and adjust all of these as a group. There we go. I've got 44 pads. It looks roughly like the drawing, but not exactly. I'm going to place a little pin here on the top overlay layer. This will be my silk screen. This is just the dot that marks where the first pin is. So now it's a circle whose radius is the same as almost 1, 2, 2, 7. Now it's a ring whose radius is equal to its diameter, and it's just a dot. My C2 distance here, the center to center distance on these pads should be 12.3, but because I've added, so 12.3, but I've added 0.25 to that on both sides, so it should actually be 12.8. If I divide that by 2, because my part's in the middle, should be 6.4 millimeters in either direction. So this needs to be 6.4. Minus 6.4. 6.4. And minus 6.4 millimeters. So now I've got all of my pads in the right place. I can put a line on the top layer just to denote where the package will be. Okay. So put a line. And then I can adjust my, come on. So that's exactly at 10 millimeters, which is the package size. So now I've got pin marking. I also got a little diagonal mark on number 1 pin. I don't think I'm going to have any luck finding a 3D component for this, so the 3D view will just be pads and silkscreen with no component. That's fine for now. This is a 44PQFP. There we are. We can save that. Back to the schematic and make sure that this is associated with its footprint. We'll go here, we'll add the footprint. Where did I put that? 44PQFP. So there's our preview. It's not amazing, but it looks like the right thing. Right. So now I can go and I can put this in my schematic. What is that? HV. Sort by name, please. Oh wait. There's the name. Here we are. This is a monster part. And this schematic will probably just be the two of these. So I can start with supply. 12 volts. These are kind of interesting because they're a 12 volt part. I'll also put my ground. And then I'll be level shifting from 3 volts up to 12 with a small, probably a single transistor level converter. I'm going to take the data out from here, run it to the next one, and then I'll run the data in to this side of the schematic. And then I'll run the rest of my inputs kind of the same way. I think I'm just going to run these down below. So I'm going to take the blanking, the polarity inputs, and the latch enable inputs, and I think all of those I can just use in parallel. I don't need to do anything special with them. Same with the clock inputs. I'll drive the clock for both of these. The clock for this, or the output from this, is unconnected. And now I have 64 channels of open drain drivers to drive my Nixie tubes. I'm going to rename this net to high voltage HV on my boost converter schematic. just because I sort of expect it to change a little bit. So now I can put high voltage supply for each tube somewhere up here. I think I'm going to need a high side resistor. If I go and look, let's see, where did my data sheet go for the Nixie tubes? They say a 30 kilo ohm resistor if you're driving from the minimum of 200 volts. Do I have a 30K resistor? I have a funny feeling I don't have one in my component library yet. That will have to come later. In the meantime, I can wire these up. Oops. I didn't want to close it, I just wanted to hide it. So from here, I'm just going to start wiring this up. And kind of being aware of the fact that if I can, wiring these up sequentially will make the software that much easier. Clearly, though, I'm going to need some more space, because now I've run out of space to route these wires around. If I move this, I can get it to do a little bit, but not move far enough, I think. So I need to move that. Move that. I think I'm seeing a pattern here. Oh, did not mean to do that. Fine, that. And now we can run these all straight down and not have to do a bunch of zigzags. Okay. I like how that works. So go down there, and then my anode lead will have to run here, and then I'll have to put a resistor in there. So I can run those around the top and immediately run into the same problem I ran into before, where I have to zigzag these across the bottom to get the schematic to look reasonable at all. I think the only appropriate way to do this is to reduce my grid size on my schematic and pack them in tighter here. make sure that that's still readable. But now that the grid size is smaller than the pin spacing, oh, come on, come on. Now that that grid size is smaller, I can fit these in a little bit better. I did not want to move that point. There we go. What can I say? There we are. There's two. Bigger, so I can drive these easier. That looks a little bit more consistent. So now this is going to be fun. This one actually will run. I'll be able to drive this from both of these without any issues. Lots and lots of drawing wires on a schematic. And right there is where I get out from underneath the zigzag from the previous component. And bring the next one down here and start doing the same thing. The nice thing is, these are all just lines on drawing, and they'll come out as traces, and I won't have to actually I won't have to do a lot of extra manufacturing work. Alright. That was not too hard. This is a little ugly, so I'm going to see if I can clean this up a little bit. So I should be able to move that over, that over. Okay, that can go. And we'll just redraw those. How far over does this need to come? let's see. Well, now I have to zigzag these over. But that's not too bad. I'll do that. I'm going to adjust the heights on all of these so they're all consistent. Okay. And then... that was not quite what I wanted. And now I can move this over by a substantial amount. And some of this can go away. And I can still leave a little bit of space here. That's just going to be a problem if I keep trying to move it. That looks significantly cleaner. Now I can move this over a bit. And take out most of the zigzag on this side so that I can make more of these pins less difficult to get to. Nope, did not want to double click there. I think I'm just going to keep going with this until this is straightened out. There, that'll be perfect. Now I can put that back, and I'm all set. And I have an extra whole pile of inputs. What is that? 24 outputs that I can use to drive other parts of my circuit. I guess these, oh, so I'm missing a high voltage here, I'll put that back. So these will be the pull-up and the current limit resistors for these tubes. Line those all up on grid lines so they all look consistent. And at some point I'm going to have to come back in here and put in... Ugh, that was silly of me. No. Yes. There. Anyway, as I was saying, I'm going to have to come back in later and put in the current limit resistors. But that won't be too bad. Oh, hello, Katrina. Oh, hello, Sam. There's a cat behind me. He's come to say hi. Hi, Sam. This is my cat, Samson. He likes to help me design circuits, but mostly he just sits on the keyboard and keeps me warm. Goodbye, Sam. Goodbye, Katrina. Are you going to bring me a cat? Oh, I've got a cat now. Hello. Oh, hi, Sam. I think Sam has made an appearance on every episode so far. Now you can all see Sam instead of me, because he's definitely the star of the show. Oh. Yes. Hello, Sam. He likes to purr very loudly, too. I don't know if that'll pick up on the microphone or not, but he's getting comfy. Alright. So I think that's most of what I'd set out to do. The only other thing I need to do is I need to come up with a level shifter for these 5 or 6 signals here. And I can either make that from discrete transistors or come up with another way to do it. I'm a purist. That looks better. Don't judge me. I feel all of you viewers judging me for that. So I need to come up with a 30K resistor for here, and come up with level shifters for this part of the circuit, but other than that, I think this is done for the evening. Good night.